Hi guys, welcome back to Students of Chemistry. In this video, we are going to learn what is spin-spin relaxation, how it helps us to reach the thermal equilibrium, and what are Bloch equations. Come on, let's go. The longitudinal relaxation, which we have learned from our previous video, is almost undetectable. Hence, NMR spectroscopy needs a different approach. What we would like to do is, instead of measuring the spin magnetization along the field, we can measure the one that is perpendicular to the field. We can recall that the thermal equilibrium itself is a biased one having magnetizations predominantly along the field. There is no such net magnetic moment perpendicular to the field. So, how do we obtain net magnetic moment perpendicular to the field? What can we do? We have to literally turn them by ourselves. No, I am not kidding. We could do this by applying something called a radio frequency pulse or RF pulse. In this situation, more precisely, a 90-degree RF pulse. We will learn more about pulses in our later videos. When we apply this RF pulse, we could successfully rotate our net magnetic moment from along the axis to the perpendicular axis. This magnetization created perpendicular to the axis is called as transverse magnetization. As soon as we switch off the RF pulse, guess what? Our spins which are precessing at this new axis will slowly go back to its original axis. Will slowly go back to its thermal equilibrium more clearly. So they will start what we call as defacing. Slowly, these spins will have variations in their precision motion, which you can clearly see from this anime. And boom, everything goes back to the normal state again. The thermal equilibrium will be restored. That's what we too want, right? As soon as the thermal equilibrium is restored, boy, there are many transitions for us to record. For lads who still find it difficult to understand the word defacing, imagine starting many clocks at the same time. All these clocks can show same time for maybe a few months or even few years. But after few years, all these clocks slowly start to dephase from one another. They would start to show different times. It is the exact same thing. So basically, transverse magnetization means the spins are revolving around the XY axis, that is perpendicular to the applied B naught Z axis. This is the M equilibrium, which I call it as the rotating magnetization revolving around the XY axis with an angle theta. I can also choose positive x and positive y axis, negative x and positive y axis, negative x and negative y axis. There are 4 opportunities to choose, but I have chosen x and minus y axis. The magnetization corresponding to the minus y axis, we call it as m minus y or simply minus my. And the magnetization corresponding to the x axis, we call it as mx. And we all know that this theta is an vertical angle, so that the opposite angle, which is congruent to this angle, will also be theta. It is a basic mathematics. And this theta will be depending upon the precisional frequency, which is the Larmor's frequency, and the time of this precisional motion. So theta is just omega into t. And from these two right angles, we can also gather information from sine omega t and cos omega t. Sine omega t is nothing but the opposite side by the hypotenuse, which is minus my by m equilibrium from the left right angle actually. And if we rearrange this equation, we get my is equal to minus m equilibrium sine omega t. And similarly, from the right angle triangle, we get cos omega t is adjacent side by hypotenuse, which is mx by m equilibrium. And while rearranging, we get mx is equal to m equilibrium into cos omega t. And to these equations, if we add the decaying contributions of spin-spin relaxation, we will get a negative exponential. So this negative exponential will be exponential of minus t by t2. And these two equations as a whole corresponds to the spin-spin relaxation equations. And this t2, we will call it as spin-spin relaxation time constant or transverse relaxation time constant. Wonderful, right? Now we know what is spin-spin relaxation and how it helps to restore the thermal equilibrium and also the equations corresponding to the spin-spin relaxation. Now the left out part is Bloch equations. These are the classical differential equations of magnetizations, which are obtained, of course, by experimental methods. This Bz, By, Bx are magnetic fields. This magnetic field can either be static, that is along the z-axis, it doesn't rotate, or rotating along the x and y axis, which rotates. From the previous diagram, if we replace all the magnetizations with magnetic fields, we will replace minus my by minus by, mx by bx, and m equilibrium by b1, as it is a rotating magnetic field. And the previous equations will follow the same, only difference is replacing mx and my by bx and by. And if we substitute the bz and bx and by in this differential equations, bz is nothing but b naught, by is minus b1 sine omega t. If you substitute, you get plus mz b1 sine omega t. Bz is again b naught, bx is b1 cos omega t. And substituting by and bx, you will get this equation. Altogether, these equations will look like this. If you add the relaxation contributions to these equations, the mx and my will be corresponding to the spin-spin relaxations, because xy axis corresponds to the spin-spin relaxation, and while the z-axis corresponds to the spin lattice relaxation. Mz minus m naught by t1 is the contribution. In mx and my, we doesn't neglect the m1 from mx and my, because these mx and my altogether combine to give m1, and neglecting m1 from mx and my is inappropriate, right? So these three equations altogether, we collectively call it as Bloch equations. So that's it for today, guys. If you like this video, like, share, comment, subscribe, hit the bell icon. And if you have any queries, contact me through my mail ID or in the Instagram account or Quora space. I'm your SSN. You have watched Students of Chemistry. I will meet you guys in the next one. Thank you.